Okay, according to my watch, it is now 10 o'clock in the morning, so good morning, welcome to Physics with Keith on this Saturday morning. I am over the moon because I've had some questions sent in, so I've got something to talk about, which is really good news. I also checked the statistics for the Facebook and the YouTube channels earlier on, and here are some statistics for you. We now have 99 people following the Physics with Keith Facebook page, which I think is incredible. And 51 people have subscribed to the YouTube channel, which is still wonderful. If we can get some more subscribers, 100 subscribers, then I can have a shorter URL on the YouTube channel, which will make it easier for me to share with people and easier for other people to hear about this. So if you're watching and you're not subscribed, please do consider subscribing, and do share this with everybody that's around. Share it with your friends, and hopefully we can get a few more people watching this and benefiting from this live stream. A reminder, this is a live tutorial. Last week there were a few people that were getting involved in real time, typing away, and they got frustrated that they couldn't type a message as quickly as they wanted to because I had slow chat turned on. Well, I've now turned slow chat off. So you should now be able to type things into the chat window and get, and there won't be a delay or a restriction on how many of those chat messages you can put. So I'm just going to type the little message saying hello out there, so hopefully you can see where that appears on the chat window. If you're out there and you're watching this live, please, drop me a message on the little chat thing so that I know you're out there, and then we can do some live tuition, asking questions, getting answers, that sort of thing. I can see already I've got a few people who have tuned in. So my apologies if I've said anything that you've missed, nothing important, but feel free to watch the start of this live stream. It'll be recorded, so you can watch the start bit again when you, if you want to, when you come back. So let's have a look at these. Oh, hi. Okay, Freya's back. Hi, Freya. Good to see you again. And I've turned the slow chat off for you. I don't know if you caught that when you got in. You said it caused problems last week, so I've turned that off. Right, the first three questions I want to look at are for a student that sent a message in, and they are A-level questions. And I'm aware that not everyone watching this will be A-level students. In fact, I'm aware of at least one who's definitely a GCSE student. So I won't spend too long on these A-level ones. I'll go through the answers. But on two of them, there are bits of knowledge that are actually at GCSE level. So the first one I'm going to look at, which is this question, is just for A-level. There's very little, there's no GCSE knowledge there at all. So if you're a GCSE student watching this, I'm really sorry. There's not a lot I can do about giving you an answer for this, but feel free to watch the video anyway, but you might be getting bored for the next couple of minutes. So here we've got three situations, and what we've got is two-dimensional pieces of metal. We can assume they're all the same depth in a third dimension, and they all have the same free electron density. It says charge densities are depicted, and so we've got plus sigma, plus sigma, plus sigma, plus sigma. But over here, we've got minus sigma and minus sigma. So these pieces of metal all have the same charge density in terms of the magnitude, but this piece of metal here has a charge density that's negative sigma, and these two have charge density. Sorry, this one's charge density is positive sigma. So maybe these are not metals. Maybe these are insulators that we've charged up somehow. It doesn't really matter. They could even be conductors that are charged up, but they're kept separated by insulators. It doesn't really matter. We've got some point here, O, and we want to measure the potential. Now, for GCSE students, you may have heard about potential difference, which is another name for voltage. Potential is something that physicists, and further down the line you get, the more interested we get in potential. In fact, we get to a point in physics when you leave A-level that we stop talking about energy altogether and start talking about potential. And it's closely related to the idea of energy. So what we've got here is a point in space, and we want to know what the electric potential is at this point and work out which one of these has the highest electric potential, which one of these has the lowest electric potential. Basically, this is multiple choice, and there are 5 options below. So which one of those options is correct for these 3 pictures? Now let's start with this one on the right here. Now this one on the right here, if we ignore this segment down here, we've got a positive charge on the right top up here. Let me get my hand icon out. A positive charge up here and a negative charge down here. So at this point in the middle, if those were the only two segments, the potential would be 0. The potential would be 0 because when we add up the potential from every tiny part up here and add it to the potential of every part down here, they're not cancelling each other out. The difficulty here is if you wanted to work this out analytically, we'd have to use calculus and do an integration over all these different parts. You don't actually have to do that. You can get a feel for this question as an A-level student without having to do that integration, which is good because calculus isn't actually on the A-level physics specifications. You're never going to be expected to do it. So what we've got here is this blob here, and the only bit of charge that has any consequence is this bit on the bottom right. And there's less length of this bit on the bottom right than there is anywhere else. But more than that, this bit on the bottom right is negative, where in these the left and the middle pictures, the charge is positive. So where you've got a negative charge, you're going to have a negative electric potential nearby. And so I know that the voltage, or the potential should I say, at 0 in this right-hand picture will be the most negative of them all. It will be negative, and therefore it will be the lowest value. So when we look at these pictures, we need to see VC smaller than everything else. And there are some options for that. We've got option, 2 and option 3. It can't possibly be option 1 because there's no way the potentials can be the same. And we can see that because this potential is negative and this potential, which is near positive charges, has to be positive. So there's no way they're the same. It can't be 3. It can't be 4 because that says the potential at C is the greatest one. And it can't be. There's less charge there nearby for a start. Remember, this charge and this charge cancel out. So there's less charge there for a start. And it's negative, so it's going to have a negative potential. So there's no way it can be 4. And if we look at 5, it's a similar picture. VC has to be the smallest one because it's the most negative. So it's either 2 or 3. Now, if we look at A and B, the length of this piece of whatever this material is here is shorter than the length of this. So because the charge density is the same, that means there's actually less charge on this left-hand picture than the right-hand picture. But also, the charge that's over here at the extreme ends of this object are further away from O than the charge nearby. Whereas in this picture, all the charge is the same distance from O as this closest point. So the fact that B, the charge is all closer on average, and on B there's more charge, means B has to have the most positive potential. And the only one of those options that has B as the biggest, VB is the biggest, and VC is the smallest is option 2. So it's got to be option 2. Okay, so that's the A-level question done with. So if you're a GCSE student and you had your fingers in your ears, then you can now take your fingers out of your ears. These are still A-level questions, but there's a lot of GCSE knowledge in here as well. So I'm going to start asking some questions and maybe I'll be able to get some answers from you. Let's start with this circuit on the left. The circuit on the left, if you are in the United Kingdom, you won't necessarily recognise this symbol as a resistor. This is a symbol that's popular in some other parts of the world, the United States, for example. I believe they prefer, actually, I think everywhere in the world prefers this symbol for resistance, except the United Kingdom. But that's a fixed resistor. And we've got this thing here, which is a cell or a power supply. I is the current that's flowing around this circuit, and then we're told about something called R. Now, GCSE students, you haven't heard about this little r before. This little r is called the internal resistance. Every power supply that is giving electrical energy to a circuit has some internal resistance as well. You can't have a power supply without internal resistance. In the very basic level, the power supply has wires inside it as well, and those wires have resistance. But there are far more reasons for there to be resistance inside our power supply. So, to GCSE students, if you're playing along live, I'm going to want you to comment something in a second. What is the total resistance in this left-hand circuit when we've got an internal resistor of R in series with a load resistor of big R? What is the total resistance in this circuit? What do you think it is? Now, A-level students, you can play along as well. It's just I know GCSE students can play along with this. The total resistance in that circuit. If you don't know, take a guess. It's online. No one knows who you are. It doesn't matter. Okay, remember there's a 7-second delay, so I'll count 7, and if no one's responded, I'll move on. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Okay, no one's playing along. That's a shame. Okay, the answer would be big R plus little r. When you have resistors in series, you add their combined resistance. Their combined resistance is the sum of those two resistances. So in the left-hand circuit, the total resistance of this circuit is R, big R, plus little r. So now look at the middle circuit. What is the total resistance in that middle circuit? Okay, there's two resistors with resistance R, and there's the internal resistor R. So when I add these resistances together, keep it simple, what do I get? 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Okay, no answers have come through. So the answer to that one would be big R plus little r, or 2 big R plus little r. In fact, let's write some of these down. The total resistance on the circuit on the left, I'll write this in red somewhere, is R plus R. The total resistance for the circuit in the middle is 2 big R plus R. Right, let's look at the circuit on the right. This is where GCSE students, I may lose you slightly, because with the new course, you need to know qualitatively what happens when you combine resistors in parallel, but you don't have to know quantitatively what happens. When I say qualitatively, I mean you need to know whether it goes up or down, but you don't have to know by how much. You don't have to be able to put a quantity on it. So, do you happen to know what happens? I can see the number of concurrent viewers has dropped, so I'm not going to pause, I'm just going to keep going. The combined resistance... not a problem, I understand. Sorry, I've just had a message through that the person who's spectating, Freya, her internet had cut out. That's a shame. I'm sorry that you missed out some parts there about the resistance adding together, but let's look at the right-hand circuit. Do you know what happens when you add resistors in parallel? You did get B right. That's good. That's encouraging. So, do you know what happens when you add resistors in parallel? Okay, first of all, do you think the resistance of the combined resistor goes up or down? So, 50-50 chance. I've got resistors. I add another resistor in parallel. What happens, do you think? Well, have a guess. What do you think happens if I add another resistor in parallel? Do you think the resistance goes up or down? Okay, up. I can see why you think that, because there's more resistors, but in fact it goes down. Yep, okay, so somebody called Frugal Dad, OC Frugal Dad, says it goes down. You are absolutely correct. The resistance of the combined resistor goes down. Why is that? Because there's more routes that the current can take. The current can either go the top way, like this, or it can choose to go the bottom way, like this. Now, if you think about this as a... like a canteen dinner queue, where each resistor is a till, and you can't get through until you've paid for your food. And when there's only one till open, the queue backs up because the current, or the rate of flow of people buying chips, is not very high. As soon as you open the second till, even if each till is only serving the same number of people per second, actually the total number of people per second that can be served goes up. So the overall resistance to serving people goes down. I'm hoping that sort of maybe helps a little bit. Now, quantitatively, GCSE students no longer need to know this, but if you have two identical resistors in parallel, the resistance of this bit becomes a half of the resistance. But don't forget, I've also got this internal resistor, which is in series with this parallel branch, so I have to add that series resistance on as well. It's a little bit complicated. I know it's a little bit complicated. I'm going through it quite quickly. Absolutely right, Freya. In fact, knowing that there's a 7-second delay in what I've said here, that means you wrote your answer before I said the answer, so congratulations. So that's sort of it. So the question is, which of these expressions at the bottom is correct? And if you look at these expressions at the bottom, they're all in terms of current. But luckily, each of these power supplies has exactly the same potential difference across it, which is labelled here as a capital E. E, short for EMF, which you may have heard about in GCSE level, you should have heard about in A level. EMF, or electromotive force, which unfortunately is named wrong because it's not a force, it's not measured in newtons. EMF is just a fancy name for the voltage across a power supply. And that's the power supply part. So that's ignoring the internal resistor. The voltage you actually get when you put a voltmeter across a battery will be lower than the EMF because the internal resistance will take a bite out of some of the available voltage. If I draw a little circuit on the right here to try to make that clearer, if instead of having, that's a bit too far to the right, you can't see that on your screen, I'll do it underneath and I can delete it afterwards. If I draw my circuit with the internal resistor, let's take the left-hand example. If I draw my internal resistor actually as a little resistor, and the notation here is a capital E for EMF, and here's my load resistor, like this, then I hope you can see that if all of this part is inside the power supply, the battery, the power supply, whatever, then I can only connect a voltmeter across these two outside bits here. And therefore the voltage you measure there will be the EMF minus whatever voltage has been lost across this middle, this little internal resistor. Now, how do I find voltage if I know resistance? There's an equation. Do you know the equation that relates voltage to resistance? I'll give you a clue. It also includes the quantity current. So the equation that relates voltage to current to resistance. Type it if you know it. Waiting a few seconds in case anyone's typing it now. You don't know that? That's okay. That's not a problem. I will tell you it. So the equation, sometimes it's called Ohm's law because it's the equation that is true if you have a fixed resistor and a component whose resistance doesn't change as the current through it changes. It's called an ohmic component. That is something you'll cover at GCSE level, but we don't need to worry about that at the moment for this question. The equation is V, the voltage, equals I, the current, multiplied by R, the resistance. And what's actually happening here is for a certain resistance, the more voltage I put across it, the more current I get through it. So the current is determined by the voltage across a resistor and the resistance of the resistor. So with that equation in mind, the voltage across from this point to this point, which is a voltage across the external resistor, I need my hand because I'm using a tiny dot. The voltage from this point to this point, so this is the sort of the outside voltage of this power supply, is just going to be V, which is going to be equal to the voltage we picked up, which is E, minus whatever didn't actually make it out of the power supply, which is IR. Remember, I times R is a voltage, but this is the voltage lost in the power supply. Now that equation is usually met in year 12 of A level. You do not have to worry about it for GCSE level, but I'm hoping that you've had a little bit of a taste of this and see actually you can use GCSE knowledge here. The idea that voltage is current times resistance, and the idea that whatever voltage you pick up in a power supply you have to drop off in your resistors, means you can conjure up this equation yourself. Okay, so why was I saying that? Because the expressions at the bottom here are all in terms of current. So for me to be able to find a solution, what I need to do is to, rather than writing these resistance equations, I need to write my equations for current. And so what I want is an expression for what the current is for each of these current I1, I2, I3. And actually what I'm going to do to make this a little bit easier is I'm going to work out what E is in terms of the values I've got, because E is the same for each circuit. So that means I can just write E equals, remember E is a voltage, voltage is current times resistance. So my current here is I1, this is in the first example on the left, and the resistance is R plus R. Now because that's the voltage across the power supply, now because it's the same for the next circuit, I can say that that actually equals I2 multiplied by the resistance of the second circuit, which is 2R plus little r. And again, in the third circuit, the voltage is exactly the same, E, so that's going to equal I3 multiplied by the resistance, which is half R plus little r. So now I've got these three these equations, and I don't even need the first part, the E part, anymore. I've got my equations for I, and I can see from these expressions that one of them must be right and the others are wrong. So have a look at my little notes here, because I did answer the question this morning whilst I was eating my cooked breakfast. Ah, yes, okay. So let's look at these expressions at the bottom and see which ones we can eliminate straight away. First of all, we can eliminate expression 1, because it talks about 2i. I is not defined anywhere in this question, so there's no way this can be the correct answer. We've got an I up here, and I don't know what I means. So next, let's look at the next ones. Note here. Let's look at number, which one is the correct one? No, okay. So let's look at number 2. In number 2 here, we're saying I is, so I2 is I1 over 2. So if we look at the expression here, we're just looking at this part first, and we're looking at this part first. Okay, so we're saying that I1 times a half equals I2. Does that look right? So let's rearrange this expression. I2 equals, and then we're going to divide through by this part. So I'm doing quite a lot of algebra quite quickly here, so I will slow down in a second. I'm just going to get it written down first to show you what the answer would be. Okay. So what I've done there is I have taken the expression which is in the red brackets here, divided through by this term here, and it's given me this expression on the bottom. If you're not very comfortable with algebra, that's an awful lot in one go. And if you're a GCSE physics student, the likelihood is that you're not familiar enough with algebra to be able to rattle through that as quickly as perhaps an A-level student could. So I hope you don't feel intimidated by what I've done there. Some people think about it in terms of moving that bit I've highlighted in yellow. So I've effectively moved it to the bottom here to get this expression underneath. I2, which is left by itself when I've moved it, equals I1 multiplied by, and then R plus R over 2R plus R. Right. Anyone that's watching, and there's 2 of you watching, could you please give me maybe a thumbs up or a thumbs down? Give me some indication if you're okay with that step, or if you want me to go into the algebra a little bit. Oops, I've deleted the wrong part. The algebra a little bit more. Because I don't want to assume knowledge, and I'm here to help you with your physics. So if it's this step that's going to trip you up, I need to know about it straight away. Don't forget this is live, so if there's something I type and you're not quite following, don't just sit there and, yep, someone gets it, that's good, well done to Frugal Dad. So during this session there are people of, yeah, well done Freya, there's people of different levels of physics, so I don't want to assume anything. Right, now, is it possible for this part that I'm about to highlight in blue here, is it possible for this to equal a half? Because if number 2 is correct, for I2 to equal half of I1, this part has to equal a half. Is that possible? There is one scenario where that is possible. Does anyone know what it is? Okay, so if you were typing an answer, that's super. If not, then don't worry about it. When the internal resistance is 0, So r plus 0 is just r, 2r plus 0 is just 2r, the r's would cancel and leave with half. And in fact, you can do exactly the same approach with the second part here, although if you look really closely, this says I, yeah, well done. So this part here says 2i subscript L rather than 2i subscript 1. But if we assume that's a typo and that's supposed to be 1, it's actually, that also tracks if internal resistance is 0. So if the internal resistance is 0, option 2 is possible. However, and so we'll keep that in the back of our mind. However, I've looked ahead and I know that there is an answer here that doesn't rely on internal resistance being 0. And we know, practically speaking, it's impossible to get 0 internal resistance. So although theoretically we could say that answer's correct, the second answer's correct if internal resistance is 0, from a practical point of view, no, that's not possible. Okay, so now let's take all my red stuff off here, get back to that expression we had before, and let's look at number 3. So for number 3, we are saying that I3 is the smallest. So if each of these expressions is equal, if this expression is equal to this expression, which is equal to this expression, then what we are saying is that if, and I'll just get this down like this, if I3 is to be the smallest part, and we'll just compare I2 to I3 at the moment, so we'll ignore, and I'll just get a bit of red here and just erase that. We'll ignore that one for the moment. Let's just look at the right hand part here. I2 bigger than I3. So if I2 is bigger than I3, so I3 is the smallest, then this part has to be the biggest out of these two. Okay, this one has to be the biggest, this one has to be smaller. Okay, and I think I've got that the right way around. I3 is the smallest, so that has to be the biggest. Okay, so is that bigger than that? Is half r plus r bigger than 2r plus r? No, and in fact I could put any numbers I want in that. That's nonsense. That's not going to work. That's nonsense. There's no way half... Pick a number. Pick r equals 2 and little r equals 1. It just doesn't work. So I can eliminate that as an option. And you can see I don't have to look at the other side of that. I know straight away that that's wrong. Okay, hopefully you're still following that. It looks like I'm getting the right messages coming back from you two who are here today live. That's good news. So let's move on to part number 4 then. So part number 4, we've got this expression here. Is this possible? And I've written some working here to help me so that I'm not sort of floundering and trying to work it out on the fly. We want to get an expression. Let's just start with the left-hand bit. Here we want to get an expression I2 equals some factor of I1, and we already had that before. That was our r plus r divided by 2r plus r. I should say big R and little r so that, you know, if people can't see what I'm doing, I'm not being horribly vague. So here's our expression. Now this is saying that this factor here has to be small. It says here smaller than, greater than a half. Okay, I think I've got that the right way around. Yes, I think so. In order for I2 to be greater than a half of I1, then that bit there has to be greater than a half. It has to be. No, you're right, Freya. This one doesn't work either. And it's for the same sort of reason. And you can plug numbers in if you're not convinced. There's no way I can get that. You could just see it. It's because of that plus little r that's the problem. There's no way that that number can be bigger than a half. So, yeah, 4 can't work either. And so the last one is number 5. Take out my cheat sheets. Here's what I did earlier. And does number 5 work? Yes, actually 5 does work, and it's the same approach. In number 5, what we're going to do is we're going to look at the expressions I've got here. Let's pick the first one, so I2 and I1. In fact, that did work. It was the second part here that didn't work. I've been clumsy, but I'm going to move on anyway. The answer is this one. I wonder why I've been clumsy in my working there. Maybe now isn't the time for me to look at it again. Well, no, that's not the time. It was the other one, I3 and I2. I made a mistake in that previous step, but I am going to move on anyway. Here, you end up with an expression when you look at the second half of this. So I3 has to be smaller than 2I1. So I3, if we say I3 equals I1, the factor becomes R plus R divided by, and this is half R plus R. That's the factor here. And so the question is, can this factor be less than 2? And the answer is that yes, it can. If you plug numbers in, you can convince yourself of that. For example, if we say little r is 1 and big R is 4, we end up with 5 over 3, which is less than 2. And what's got underneath my logo? I can move my logo, or I can move that. But anyway, so it's, yes, I made a mistake with the previous step. That's going to irritate me. It's this part that doesn't work and this part that does work. So it's looking at those inequalities, and if you're ever not sure, little tip for you, just throw some numbers in and see what sticks. You don't have to get bogged down too much with this. It's not too tricky if you just throw some numbers in. Right, the next one, this was also sent to me by this student saying this is A-level physics, and there is an A-level physics way of getting an answer here, but I've got to warn you, this goes a lot more advanced than A-level physics. So I'm not sure where this question came from, but if you want to do this quite formally, I can't see a solution that doesn't involve going into Lagrangians. Now, as I haven't taught Lagrangians ever, and the last time I used them was more than 10 years ago, I can't remember them and I have to look them up. And knowing that they're not on the A-level spec, because 1, I'm an A-level examiner, and 2, I'm an A-level physics teacher, I know that that's not going to be necessary here. So I looked at this question and thought, is there a way of finding which of these multiple choice options is correct without having to go into undergrad level physics? So what we've got here is, I'll just describe the problem to you as I interpret it, and there is some ambiguity here as well, which I don't think helps. We've got a mass which is sat on a surface, but the surface has friction. Now, in A-level physics, you don't have to deal with coefficient of friction. You might have to you don't have to in AQA physics anyway. But for just for A-level mathematicians, if I say, let's call this my frictional force. Frictional force is going to be equal to my coefficient of friction multiplied by the normal force, which in this case is going to be the weight of this. Normal means right angles. So there's a force down. That's a badly drawn arrow. That's not very straight down, is it? There's a force down here, which is the weight, which is nothing to do with the horizontal motion at all. But because there's that force down, the frictional force is greater the greater that mass is, because it pushes harder on that surface. And the coefficient of static friction, which I believe is in fact a tensor, but you don't do that yet, not until undergrad physics, is given to you saying that it can have a... it says this is always bigger than, so that means it takes a minimum value of this. So mu has a minimum value of u squared over 2g L naught. So what's u? U is the initial, and I think it says speed, so it's a scalar, the initial speed when x equals 0. And here's some ambiguity. Is x equals 0 when it's at this position here? Or is x equals 0 when it's at this position here? And it does actually matter. The way it's written, I don't know. I do know that the length of the string, which is elastic, so the original length of the string is L0. So when the string is fully extended, but not being stretched at all, so there's no elastic force pulling back on that block, then the distance from this left-hand edge is L0. And hopefully, you can see that lovely script writing for L. This is a pretty standard way that physicists and engineers would write an L so that you can easily tell it apart from the number 1 or the uppercase I or a modulus sign. What we do is we write out L like this. So we've got our we're adding to our diagram here, and I don't know where x equals 0. So that's the first problem I've got. So they've got this initial velocity. For some reason, the coefficient of static friction here is given as having a minimum value, which somehow depends on that initial speed. This seems completely nonsense to me. I cannot see why this would be true. Unless, of course, u here is the speed at a given time, not the initial speed. In which case, rather than saying this is the coefficient of static friction, this would just be the coefficient of friction, which would take a value of 0 when u equals 0, and that would be the minimum value it could have, which would make physical sense to me. However, it's not what the question says u is. So either u is badly defined. I don't know where this question came from, by the way, but I've never seen it on a past paper in A-level. A student just sent this to me asking me to look at it, saying it was an A-level question. I don't think it is. May have come from an older textbook where A-levels used to be difficult. So anyway, this is our expression for the friction force. We also have the force that is experienced when this spring is extended beyond the length L0. Now, have you met Hooke's law before? If you've not met Hooke's law tells us that the restoring force on this elastic string, yes, Frugal Dad has, the elastic force on this string is proportional to the extension of the string. So the more you extend the string, the greater that force it feels back. Freya hasn't, but that's okay. You do encounter it at GCSE level. I believe in most examples it's now a required practical, which are difficult to do at the moment whilst we're in lockdown. I have in fact got a simulation. I'm just going to bounce the screen across onto my face while I load it up. Otherwise you get to see my desktop and you probably don't want to see that because it's a mess. So let's go to forces and Hooke's law. Okay. So courtesy of Dr. John Nunn, who very kindly gave me permission to use these in these tutorials. Here is a little simulation of a spring. Hopefully you can see that okay. And I can add more weights onto the bottom of the spring. And as I add more weights, so there's more force pulling down on that spring, it reaches a stable equilibrium when the force that is pulling down on the bottom of that spring is equal to the force pulling up on the bottom of that spring. And the force pulling up on the bottom of that spring is this elastic force from this spring itself. So I know what that force is because I can just look at what I've got here. If I've got 6 half-Newton weights, that's 3 newtons pulling down on the bottom of this spring. And so for the spring to be not accelerating down, the bottom of the spring not to be accelerating down or not to be accelerating up, that means the up force on this part of the spring also has to be the same, which is 3 newtons. So what Hooke's law says is that if I double that force, I double the extension. So my original extension going from about 7 to about, what was that, 10-ish, so 3 centimetres. If I go up to here, I'd expect it now to be more like 6 centimetres, and it is indeed more like 6 centimetres. So that's Hooke's law. And the expression is written on the top of this little simulation. The force, the restoring force on a spring, is equal to, I probably should have a minus in here because the extension is in the downward direction, but the restoring force is in the up direction. But let's not get worried about that either. So the restoring force in the spring, the magnitude of the restoring force in the spring, is equal to the spring constant multiplied by the extension of the spring. The extension of the spring is how much longer it is. So when this thing has stopped bouncing around, this is the original length, and there's a little mark here on the bottom of the spring we can use to make our measurements from, called a fiducial mark. The extension is this extra bit of length that the spring takes on. So that's a spring. This is a string, not a spring. So because it's a string, because one of my first thoughts was this thing's going to oscillate until it loses energy through dissipation due to the friction on that surface. However, it's not going to oscillate if it's just a string, because there's going to be no compressive restoring force. So this thing's moving to the right initially. It's going to move to the right, slow down, slow down, slow down, and stop. And then it might even start moving to the left and then stop. What it's not going to do is oscillate. So we're not in the realm of harmonic motion, which is very much A-level, not GCSE. Doing mathematics with damped harmonic oscillation doesn't really come up at A-level, but I can't see why it wouldn't if you assume exponential damping. So what we've got here is a restoring force. I'll call that Fs, the force from the string, which is going to be equal to the spring constant, which is given here as a capital K, multiplied by the extension. And here was my second problem. If x is labelled as 0 here, then the extension is just going to be x. However, if x is labelled as 0 at the very beginning over here, at the very left, then the extension is going to be x minus the original length. And I don't know, I don't know from this diagram or from this description which it is. It's ambiguously worded. I think that x is 0 is here, and so this just becomes that. But it might not be. It is a badly worded question. Now, those are the two forces. It would be lovely if we could just say, when those two forces are equal, this thing doesn't move. But that's not the way it is, because this thing is going to be moving towards the right, and as it moves towards the right, the force of friction acting left is initially going to be high and is then going to be dropping. And the reason for that is that the force of friction is going to be related to the speed. And we know that's true. The faster you move, the greater the friction force. And all I know is that friction is going to have a minimum value of this, but I don't know how the relationship is dependent on speed. Unless u is just the speed and not the initial speed. But it says over here, it's the initially moved with the speed of u. So I don't have enough information about how mu depends on speed, which is a problem. It's a really badly worded question. So as this thing is moving to the right, friction's going to reduce, but the restoring force Fs is going to increase. And then what's going to happen is those two forces are going to end up being balanced, and I'll stop moving. I'll stop. But because the friction force is going to be reducing as it moves outwards, I don't know if when the friction force is equal to 0, it's then going to have to move back because the restoring force is going to be... that wouldn't happen, actually. So we're going to have these two equaling each other. I think that's the bottom line. But I don't know. I don't know whether this is... whether this is even right, because I don't know if I've interpreted the question correctly. So at this point here, we're going to stop. Now, everything's going to stop moving. Now, if you look at these questions, these possible answers, there's a clue here. There's a u squared. There's a 1 over 2 u squared. There's a u squared. Where on earth does u squared come from? Well, I can see that u squared is given in mu, but then each of these expressions also has a mu in them. So I can't substitute for mu without losing my mu. So this is a problem. I thought, well, where's the u squared then? And the only thing I can think is that we need to talk about work being done. So the initial energy that this mass has is a half mu squared. That's GCSE level. That's the kinetic energy, which is half mu squared. It's u because it's the initial speed squared. And so we're now doing work. We're doing work against friction as this thing slows down until it stops. And we're also doing work against this force that's pulling back in the opposite direction. So we're doing work against the resultant force. Now the force, I'll say that I'll call this, no, I don't want to call this sigma F. Let's just call this F. Let's just call F the resultant force. Is going to be FR plus FS. In fact, we've called the right direction positive. So let's say it's going to be minus FR minus FS. Okay, that is, both forces are going to be acting to the left initially. And again, I don't even know if this starts from a position where the string is fully extended. I don't have enough information. So if that's the force, I know that the work done, which has to be equal to half mu squared, the work done is by definition, and this is A level, the integration of F as a function of x dx. Okay. Well, I don't know what the function of this is as a function of x. The frictional force, because I'm not given enough information about how mu depends on u. I can't use any sort of simple equations of uniform acceleration that we do in A level, because acceleration will not be uniform. So this problem becomes one where I look at it and think I can only solve this using Lagrangians. But don't worry. We can still get an answer using just A-level physics, and also that physics I'm going to show you is so useful for GCSE level. We're going to do something called dimensional analysis. It's the most powerful tool in a physicist's arsenal, by far. So let's scroll back up to these questions. I might have to make this all a little bit smaller so it all fits on the screen and I can write around it. Shout at me if this gets too small for you to see. Right, let's try that. Is that bit okay? Is it a bit small, or can you see that okay still? I'm only really interested in the 5 expressions at the bottom. We're going to eliminate one at a time. So is that clear enough or not? It's okay. Good. Freya says it's okay. So let's start by eliminating some. X equals 0. No, I don't think x can equal 0. For x to equal 0, it will have returned to its original position. I don't think... Yeah, Frugal Dad can see it fine as well. Okay, so I don't think it can return to its original position, because we can have a non-zero static friction at a speed of 0. Okay? Because friction has a lower limit here with an initial speed in it. So because of that, we can have a non-zero friction force even though the speed is 0. That's what static friction is. And so because of that, this thing will reach an equilibrium. The mass will reach an equilibrium, but it will not have returned to its original position. So I think the first option is wrong. So let's look at the other options, and hopefully we can use dimensional analysis to prove that that 3 of these 4 are wrong. Now, the way dimensional analysis works is you cannot equate 2 things that are not the same physical quantity. Let me explain what I mean. When I was sort of younger, starting my teacher training almost 10 years ago now, I had to spend 2 weeks in a primary school. It was atrocious because I'm not a primary school teacher. I do not suit that environment at all. I don't know how they do it. And this primary school child, hearing I was a physicist, got very excited because he knew about science. He must have been in year 4 or something. And he came running up to me in the playground. He said, "Sir," and I said, "Yes." I don't know his name. I call him Steve. I don't know his name. "Yes, Steve." And he said, "Sir, what's bigger, the height of a giraffe or the mass of an elephant?" And at that point, my head exploded. I mean, not literally, but I had real problems because I can't say they're 2 different quantities. If I measure the height of the giraffe in inches and I measure the mass of an elephant in solar masses, then the giraffe has a bigger number. If I measure the height of the giraffe in astronomical units, that's the average distance between the sun and the earth, and I measure the mass of the elephant in atomic units, that's 1/12 of the mass of a carbon-12 atom, then the elephant gets a bigger number. But the numbers are describing physically different phenomenon. I can't compare them. It caused me a lot of problems because I can't explain that to a year 4 child. I barely can explain it to a year 13 child, so I definitely can't explain it to a year 4 child. Similarly, you cannot add or subtract two quantities that are different. So I'll give you an example. If I say to you, what is 2 meters plus 3 seconds? I can't do it. It doesn't make any sense. There's no physical sense there. It's nonsense. It means nothing. If I say to you, can you get 2 kilograms? Add 10 centimeters to that. I can't do that. It's nonsense. And so physicists quite early on worked out that their universe can be, all physical phenomena in the universe can be described by a small number of unique quantities, what we call dimensions. And they are length. So we can describe a length of something, we can describe an area as 2 lengths multiplied together, we describe a volume as 3 lengths multiplied together. But you can't describe a mass in terms of lengths. It doesn't make any sense. Mass is another one. That's one of our dimensions. Time is another one. And there are some more. We can have current. There's different systems here. Some people like current, some people like charge as a dimension. I'm not going to enter into that as a whole debate that's somewhat unnecessary. You use whatever's best for you at the time. But I actually prefer charge. So charge... I don't like including temperature as a dimension because to do so means you have to include entropy as a dimension. I believe entropy is dimensionless, but chemists tend to believe that entropy is a dimension, and so on and so on. So, okay, we don't have a complete consensus in the scientific community about what the dimensions are, but we do all agree on these first 3: length, mass, time. Charge or current, whichever one you prefer, and then maybe temperature, maybe even luminosity, so how bright a light is, that's sometimes counted as a dimension. Number of moles is sometimes counted as a dimension. But we'll leave that. So every quantity can be described in these dimensions. So let's have a look at some of these quantities. K. Let's look at K. So K, to show us something's a dimension, I'll put it in square brackets, okay? So if you see square brackets, everything in between them is a dimension, not a symbol for an equation. So K, what was K? From our equation before, K was the spring constant, which was the restoring force from the string divided by the extension of the string. Now, what is a force? A force is a mass times an acceleration. That will do. That will do for a general equation for a force. And what's an acceleration? An acceleration is a length divided by a time divided by a time. Or you could say a speed divided by a time. A difference in speed divided by a time. Speed, we'll use a v divided by a time. And a v is a length divided by a time. That's an L for a length. So we've got these very basic, very general equations, and GCSE students recognise this one. They probably recognise this one as a change in velocity divided by time. They should recognise this one as the constant mass version of Newton's second law. And this equation here comes from Hooke's law, which we'll meet if you haven't yet already. But these are basic equations. For an A-level physicist who's done GCSE, they'll be fluent in these. For someone who's just starting out in their GCSE, perhaps you'll need a bit more practice. I'm sorry, I've just realised I've gone well beyond the half an hour, so I hope you can just tolerate me for a little bit longer so I can finish this question. I didn't intend to spend an hour on these 3 questions, but I like talking. So let's look at the dimensions of V. The dimensions of V are just a length and then divided by a time. Now the notation I'm going to use here is if something is on the denominator of a fraction, so divided by, I'm going to give it a negative power. If you're a GCSE student who's never met that before, Mathematically, it's fine. Accept it for now, and if you want to ask me about it a little bit later, or maybe start next week with that, I'm happy to do so. But a negative power is the same as dividing by something. So L times t to the negative 2 is L divided by t squared. This is L times t to the negative 1, which is equivalent to L divided by t. They mean the same thing. Okay, so V divided by T. So that's going to be our L divided by T and then divided by another T. Like that. I'm just going to work my way up this list and delete things as I go along because I don't need that bit anymore. L divided by T, as I could just simplify that as L divided by T squared. Which looks like that. Okay, so now we move up to the next one. Force is mass times acceleration. So it's a mass times that dimension for acceleration. And you don't have to worry, well, about the square brackets. I could have just left these two square brackets out there, but I put them in there because this was mass and acceleration. But that's fine. That's how maths works. I can write that or I can put the brackets. It doesn't matter. Now, the last bit there then, so we've got a force which is divided by a length. So our force we've decided is mlt to the minus 2, and if we're dividing by extension, which is a type of length, that means I've got to multiply that by extension to the minus 1. So we're now left with this extension, this length here, then divided by a length, they cancel, so the length vanishes, and we end up with that for k. So that's the dimension of k. So if any of these expressions I'm trying to add k to something that doesn't have the dimensions that are the same as this, then it can't work. Okay? If I'm trying to divide k, subtract k, and so on and so on and so on. So let's dip into all of these. Let's have a look. I need to probably look closer here to see what's going on. K has mass as a dimension, agreed? So I'm going to have to make this bigger because I want to write on it and it's not big enough. I'm sorry. I know this is just messing around a little bit, but I need to give myself a bit more room. Let's hide my logo. So give myself a bit more room over here. Let's hide that. Let's move this down to the bottom right there. So I can keep that. That's what I want. Let's get rid of that X. And let's give myself a bit more space to write on. There we go. I'm happy with that. Right, okay. So now let's look at these expressions. Does x0, which is the position measured in meters, probably, it's a distance from the starting position, does that have mass in it? Or is it just a length? I mean, I've sort of led you to the answer there. It's just a length. Which means that everything on the right, when you work out the dimensions, has to be just a length. So if I'm left with a mass on the right that is not cancelled with another mass on the right, it's impossible. Let's look at the equation number 4, just because I happen to be looking at that one. K has mass. And there's a mass here as well. But there's no mass on the left-hand side. So there's no possible way, you ended up seeing my desktop anyway, there's no possible way that it could be number 4. I'm sorry, I don't have to do any complicated maths, I don't have to do any complicated Lagrangian physics or anything like that. I could say it's not that one because it's not going to return to the starting point because static friction has a minimum value that's above 0. I can say it can't be number 4 because that's got some masses on the right hand side that never cancel, and yet there's no mass on the left hand side. In fact, we can go through and do the same thing to all of these. If we look at this one here, this has got a mass here, it's got a mass here, within the K's got a mass. U squared is just a speed squared, which is a length squared divided by a time squared. So there's no way the masses cancel. So number 2 is impossible as well. Let's look at number 3. Number 3, we've got K, which has got a mass. We've got M, which has got a mass. On the top here is U. squared, again, u squared, doesn't have anything to do with mass. I've got masses on the right-hand side, no masses on the left-hand side, not possible. And the only one that's left, therefore, and I have checked it, it is dimensionally consistent, is number 5. So by a process of elimination and doing something called dimensional analysis, we can see that the answer has to be number 5. We haven't really done very much physics beyond trying to visualize the problem and understanding that it can't be option number 1 because the mass will not return to its original place. And once we've done that, the rest of this is just, well, let's check out and see whether the dimensions work. It gave me an answer. If this were not a multiple choice question and I had to come up with the expression for x0 myself, I would struggle. It would take me quite a few pages and an awful lot of Googling to remind myself how to do Lagrangian mechanics. I can't see another way around it. So, I mean, I've now been rambling on for an hour. I'm tremendously sorry that went on for double the amount of time that was intended, but I do hope it was useful. I'm very sorry as well to the GCSE students that were watching, because this week seemed to focus far more on A-level than in previous weeks. I do offer this for A-level and for GCSE, and of course it's going to be impossible to satisfy everybody's needs at exactly the same time. What I'm hoping is that by going through that, okay, Frugal Dad says, got it, thank you, that's absolutely fine. What I'm hoping is that if you are a GCSE student, you still get something from this. So it's been better to watch it than to not watch it. But if you send me some questions, just like this person did do to me, they sent me these 3 questions to work on. And it might be Frugal Dad, but the name doesn't ring a bell. And I don't want to read out the person's real name because they sent it to me in a private message, so it probably wouldn't be appropriate for me to do so. But whoever it was that sent me those 3 questions, they said they were A-level questions, and I went through them because they asked me to. But if you've got your own questions you want help with, or if you don't know any questions you want help with, but there's a particular topic, even if it's quite a vague topic that you think, right, I want to work on this, help me with this, let me know in advance, and I'm very, very happy to do so. The last 5 weeks, I think, how many weeks have we been doing this for? The last 4 weeks we've been doing GCSE. This was A-level. We can go back to GCSE, we can do A-level. It depends on what questions I get. Okay, if you're watching this and you haven't yet subscribed, please do. So, it's the other corner. Please subscribe, because if I can get to 100 subscribers, then I can change my URL for the YouTube channel, which at the moment is just nonsense. And share with your friends and send questions in. Interact. Ask me questions and I can help you. Let's call it a day. It's now 2 minutes past 11 on a Saturday. You've done a whole hour of physics on your weekend for fun. Well done. I'll see you next week, and stay safe. Let's end the stream.